In our last lesson, we were taking a look at indeterminate quotients. That is, situations where we ended up with 0 divided by 0 or something like that. In this lesson, we're going to be taking a look at indeterminate products. And here you can see an example of the indeterminate product that we're going to be taking a look at, because we have two existing rules. We have 0 times anything equals 0, but infinity times anything equals infinity. But what happens when those two collide and we try to do 0 times infinity? Would that be 0? Would it be infinity? Or would it be something else entirely? And as you might be guessing from the work we did with the indeterminate quotients, it actually could be almost anything. And at least in the context of limits like we're working on here, we're going to actually have to do the work to figure out what it would equal. In order to do that, we're going to be working through two examples. This is the first of those two examples. And we're going to be figuring out the limit as x approaches 0 from the right side. Now, at this point, you will see a number of them where the limit will be approaching just from one side. That's going to be partly because we're going to be looking at some things like that, like the square root of x. Remember that the square root of x has a limit as we approach 0 from the right side, but not from the left, because 0 is where the graph starts. So that's why it's from the right side only here. Also because natural log, if you graph natural log, it also exists only to the right of 0. All right, so our process is, first of all, try to find the limit without using L'Hopital's rule. So notice this is exactly the same as what you did before. Try what you normally would. So let's actually try that. If I plug 0 into this, what's that going to give me? Well, it'll give me the square root of 0 times the natural log of 0. Well, the square root of 0 is 0. And the natural log of 0, if we take a look at that graph, it's at an asymptote. It's actually approaching negative infinity. The limit is negative infinity as natural log approaches 0. And so we end up with 0 times infinity as a situation. That's what tells us that this is an indeterminate product, because we're doing 0 times infinity. All right, so the direct substitution did not work. Factor in reduce won't work. No conjugate to multiply by that would help. Now you do see a square root there, but remember the conjugate would require like square root of x plus 1. And even then, it would have to be part of a fraction to really be a factor there. And then combine fractions, which there aren't any fractions to combine here. So that means that yes, we are resorting to using L'Hopital's rule here. And we have a new step in L'Hopital's rule, because L'Hopital's rule only works when we can find the derivative of the numerator and the denominator separately. That means we need to have a numerator and a denominator. So if it's not already written as a quotient, then our first step is to rewrite the product as a quotient. And so that's what we're going to do first. Now, in order to do that, we have a couple options about how we do it, because I could either try to take the square root of x and write it in such a way that I can put it into the bottom of the fraction, or I can write the natural log of x in such a way that I could make it go onto the bottom of the fraction. And how do I put it onto the bottom of a fraction? Remember that anything to the power of a negative exponent equals 1 over that same thing. And so basically I'm going to be using negative exponents in order to be able to turn one of those into the bottom of the fraction. All right, well, let's take a look and see which way we want to do that in. And we need to figure out which of these two would be the most useful. So on the left here, you see where I took the square root of x and first wrote it as x to the power of 1/2. And then if I want to put it into the bottom of the fraction, that means I make it x to the negative 1/2. So by making it a negative exponent, that means I can flip it in the bottom of the fraction. Now, normally, you've been used to doing this the other way. You've been used to saying, okay, I got a negative exponent, so that means move it out of the bottom. But in this case, we're using that same rule to move it into the bottom. That way we have a fraction involved, and that's what's going to allow us to actually do the solving here. Okay, now the other way that we could do this is that we could also try moving the natural log into the bottom. So that would mean like we're going to take the natural log of x and turn it into 1 over the natural log of x to the negative 1. And so that's what we've done right here, is we turned that into natural log of x to the negative 1. Because again, if I apply a power of -1 to something, I flip that in the fraction. So it moves from the top where it currently is into the bottom of the fraction by doing that. Now we need to be able to figure out which of these two forms is more useful, because one of these, if we apply L'Hopital's rule to it, it's going to work out fairly nicely for us. And the other one, if we apply L'Hopital's rule, it's not. Now, if you already see which way is the better way to do it, then you already know how to go through this process. But if not, let's actually do the derivatives of each of these, top and bottom, separately using L'Hopital's rule, so that we can actually see which one is indeed the more useful. So on the left one, if I take the derivative of the top and bottom, the derivative of natural log of x is 1 over x. And the derivative of x to the -1/2 would be -1/2 times x to the power of negative, then I do 1/2 minus 1, remember. -1/2 minus 1 is -3/2. And so then it would still be the limit as x is approaching 0 from the right there. Remember, you still need that limit notation because we haven't done the direct substitution yet to get rid of it. Now looking at that, you're probably looking at that saying, that looks pretty ugly. I do not like that. And so maybe the other one's better. So let's check out the other one. Let's see what happens if I do that one. So I have the limit as x is approaching 0 from the right. If I take the derivative of the top, x to the 1/2 becomes 1/2 times x to the -1/2, because I'm subtracting 1 from the 1/2 there to get -1/2. And then that would all be over, let's see here, natural log of x to the -1. That looks like chain rule to me, right? Because we have something to the power of -1. So that would be -1 times that same something. And then power rule, -1 minus 1 would give me -2. But then times the derivative of that inner function. So in this case, the derivative of natural log would be 1 over x. Now, as you take a look at these two functions, these two results from using L'Hopital's rule, finding the derivative of top and bottom separately, which one of those could you clean up? Hopefully you're noticing that the one on the left is actually going to be a little bit better. The reason is, on the right side, you'll notice that I have the natural log of x to the power of -2. If I keep using L'Hopital's rule on that one, I'm just going to end up with the natural log of x to the -3 and then natural log of x to the -4. I'm never going to get rid of the natural log of x. And the natural log of x, remember, as it's the limit as x is approaching 0, it's approaching -infinity. So I'm always going to have this infinity in there if I leave that there. And so I don't want to do that. And so to get around it then, this is your better option. We are going to just work with everything there. And so the rule of thumb is that when you have an option, put the polynomial on the bottom of your fraction there. Now, you might be wondering a couple of things. Well, what if they're both polynomials? Well, first of all, if they're both polynomials, you probably don't need to use L'Hopital's rule. But let's say there was some way, well, then you could pick your choice. You could choose either one to put into the bottom there. Or what if neither of them is a polynomial? Well, you could always go back to trying each one and looking to see how it's going to work out, because the top and bottom should simplify. But there's also going to be one other thing that we can do if neither is a polynomial. And that is what we'll look at in our next problem after this. But before we get there, let's finish this one out. So now that I've gotten to this point, I want to clean that up. I need to simplify that into something much better. So let's go ahead and do that. I'm going to start by going ahead and just simplifying this 1 over x here. Now 1 over x, if I put it into just one big old fraction over here, that means the 1 would be on top of that fraction and the x would be on the bottom. Okay. Then I'm going to head over and I'm going to deal with this mess on the bottom. The nice thing about dealing with something like this, though, is that just take it piece by piece and it's not too bad. So like, first of all, I have a -1/2 in the bottom. Now, what's it mean when you have a fraction in the bottom like that? It means you're dividing by -1/2. half. Remember how to divide by fractions? To divide by a fraction, you multiply by its reciprocal. And so that tells you then that the 2 is going to be on the top, and that -1 is going to be on the bottom. And yes, technically we could have put the negative into either the top or the bottom, and we'll end up with the same answer. I just did it that way because it's a little bit easier to digest. And then we come to this x to the power of -3/2. Notice it is a negative exponent. And so the negative exponent means that that x is going to be flipping into the top of the fraction. And so then that means if I just flip that to the top by dealing with the negative exponent, it'd be x to the 3/2. Now, do I take that 3/2 and like split it up into 3/2 like this? No, because the 3/2 is all in the exponent. It's not a number like the 1/2 or the 1/x was. The 3/2 is trapped in the exponent, so it has to remain trapped in the exponent. All right, so now that we've gotten to this point, that looks like something I could clean up a little bit more, right? So this is still going to be the limit as x is approaching 0 from the right. So I got the 1 times 2 on the top. Well, that, of course, would give me 2 on the top. And on the bottom, I still have my -1. If you want to, you could actually take that negative out of the bottom, and you could just write it out front of the whole fraction at this point, if you wanted to. But again, for clarity, I'm just going to leave it there just because it helps you to track where the numbers have moved to. And then we got our x's now. I have x to the 3/2 on the top, and I have x on the bottom. Remember that when we divide x's, we subtract their exponents. So in this case, I'm going to be doing 3/2 minus 1, which of course means I'm doing 3/2 minus 2/2, which gives me 1/2. So that means that I'm left with x to the power of 1/2. Well, that even I could clean up a little bit. You know, I could just make the whole thing into -2 times x to the power of 1/2, but I don't even need to, because I can actually plug in my 0 right now and do the direct substitution to see what that would give us. Because what is 0 to the 1/2? Give you a hint. What's 0 to the power of anything? It's 0. And so 2 times 0 on the top would give me 0, and 0 divided by -1 would give me 0. And so the limit as x is approaching 0 from the right here equals 0. And in this case, it happened to equal 0, but of course remember that it could end up equaling all sorts of other things too. You have to go through the process to figure that out. So again, kind of what we saw with this problem. Once we saw that we needed to use something like L'Hopital's rule, that is, we had an indeterminate product because the whole thing started out as 0 times -infinity, then I wrote my product as a quotient, that is, I made it into division. I do that using a negative exponent. And then I used L'Hopital's rule. When using L'Hopital's rule, you're probably going to have to clean up a somewhat ugly fraction along the way. If you ever have a choice, remember, put the polynomial on the bottom. All right, so that one's done. But I did promise to show you what if one of them's not a polynomial. So that's what we're going to look at next. So in this case, we have the limit as x is approaching 0 of cotangent of 2x times sine of 6x. Again, we need to start the same way, which is try to find the limit without having to use L'Hopital's rule. Remember, we only use that when we have to. Otherwise, it might actually give us an incorrect answer. So let's actually check that and plug it in and see what that's going to give us. So I'm going to end up doing cotangent of 2 times 0. So that's going to be cotangent of 0. Well, cotangent, that's cosine over sine. So cosine of 0 is 1. And sine of 0 is 0. And 1 over 0 equals infinity. Remember, anything divided by 0 is basically going to give you infinity when we're talking limits. If I was actually looking for an actual answer, you would say does not exist. But when we're dealing with a limit, we can say that it's approaching infinity because it is limit. All right, and then times sine of 0. And sine of 0 is 0. So we're looking at infinity times 0. So yes, this meets our first criteria for using L'Hopital's rule, which is needing to use L'Hopital's rule. All right, so because right now we're looking at a product, that is, we have a function times another function. Our first step is to rewrite that product as a quotient. So we're going to make this into division. To do that, the thing that leaps out to me about this one is that I actually have a fraction in there already. I just simplified it. Because of course cotangent, remember when we were evaluating this, in order to figure out what cotangent was, we said, oh, well, cotangent is cosine over sine. Then let's write it that way. So whenever you are dealing with these trig functions, you have the option of turning it into a fraction by using those reciprocal functions and using the functions of functions like that. So like cotangent is going to become cosine of 2x over sine of 2x. Now that, of course, is times sine of 6x, but I want the whole thing to just be a fraction, right? So rather than writing it like that, I'm going to make this one big fraction, and that sine goes on the top. Because anytime you multiply something, that means it goes into the top of your fraction. Notice we now have the quotient that we were out for. Question before we go forward, though. Can I cancel out the signs here? The answer is no. The reason is because the sign on top is of 6x and the sign on the bottom is of 2x, and there's not a way to be able to just cancel those out because we're going to be doing sine of two different angles. And because of that, no, they don't cancel. So we have to operate with it from here, but we can. So we're going to be using L'Hopital's rule here, which means it's still going to be the limit as x is approaching 0. And I need to do the derivative of the top and the derivative of the bottom separately. Now the derivative of the top, yes, is going to require a little bit of work because the derivative on the top is going to require what rule? Do you see it? It is product rule because it is cosine times sine. So we use product rule here. Remember, product rule, original times derivative plus derivative times original. So for this one, original times derivative, so that's going to be cosine of 2x times the derivative of sine of 6x. The derivative of sine is cosine, so that's going to be cosine of 6x. But because it is not cosine of x, it is cosine of 6x, we do still also need to use chain rule with it. And so I then multiply that by 6. All right, then it's going to be plus derivative times original. The derivative of cosine is negative sine. So since it's going to give me a negative sign, I'm just going to go ahead and call that minus instead of plus. Sine of 2x, and again, we have to use chain rule here, so that's going to be times 2, and then times original, so that's just going to be times sine of 6x. Now at the moment, it doesn't look like we've made much ground, but hopefully when we go and try direct substitution here in a moment, we'll at least be able to figure this out and no longer get 0 over 0 or infinity over infinity or something like that. All right, but before I do that, I still have to find the derivative on the bottom. The derivative of sine of 2x, that would be cosine of 2x times 2. All right, now let's try our direct substitution again. So I'm going to be taking that 0 and I'm going to plug it in for x every place where there's an x here. And we're going to figure out what every single one of those equals. So let's just go through them piece by piece here. First up, cosine of 2 times 0. Actually, all those 2 times 0s and 6 times 0s, those are just going to be 0. So we can just go straight to what's cosine of 0. Cosine of 0, yes, you should know it off the top of your head. This is unit circle stuff, is 1. So it's going to be 1 times 6. So that takes care of this section right here. So then minus, now I'm going to do sine of 0, which is 0, times 2 times sine of another 0, which is, of course, still 0. And that's going to be all over cosine of 0, which is 1, and then that was times 2 on the bottom. And so you notice that if I simplify this, I end up with 6 over 2, which equals 3. And so that is our final answer here. This limit, as x is approaching 0, of cotangent times sine here equals 3, at least in this particular case. And so again, in order to summarize kind of how we approach this, remember that the very first thing I did is I needed to rewrite it as a quotient. In order to do that in this case, I used the fact that cotangent can be written as a fraction of cosine and sine. If I was looking at a similar problem, like let's say I had one that had, let's say, cosecant of x, I would turn that into a fraction by making it into 1 over sine of x. That same sort of thing. So use those rules that you know out of the trigonometry to help you here. And of course, once I had turned the whole thing into a fraction up here, then I was able to use L'Hopital's rule as usual, finding the derivative of the numerator and the denominator separately.